be Zhenjian, and he's going to tell us about also duality between one-way functions and symmetry of information.
This is a joint work with Shuichi Hirahara, Rahul Yarango, Mikito Narashima, and Igor Oliveira. And this work is about the connection between two things. So one is the one-way functions. I guess it is one of the most important objects in cryptography. And the other is called the symmetry of information, which is an important property of Kolmogorov complexity. And it is something that we don't have a very good understanding in the time-bounded setting. And the main result of this work is a new characterization of one-way functions using time-bounded symmetry of information. And we show that one-way function exists if and only if some average version of time-bounded symmetry of information fails. I will talk more about this in the rest of this talk. I guess we have seen Kolmogorov complexity many times in previous talks. So let me just recap the definition very quickly. So for binary string X, we want to know the length of the shortest string from which we can recover X. So the Kolmogorov complexity of X is then defined as the minimum length of string M, which is called a program. So such that if we fit M to the universal Turing machines, we get X. And we can also define the conditional variant, where we are given an additional string that helps to recover X. So the Kolmogorov complexity of X given Y is the minimum length of a program that recovers X using the string Y. And yeah, we can also define a time-bounded version of Kolmogorov complexity. So in this case, we fix a time-bound function T. For example, T is a polynomial. And the T time-bounded Kolmogorov complexity denoted by K superscript T is the minimum length of a program that can recover the string within T stats. And as we've seen in some of the previous talks, so time-bounded Kolmogorov complexity is very useful and recently has many exciting applications in complexity theory and cryptography and also learning. As I mentioned earlier, the focus of this talk is something called symmetry of information, which is an important property of Kolmogorov complexity. So let me tell you what it is. So first of all, if we have two strings, X and Y, then it is easy to see that the Kolmogorov complexity of X and Y is at most the Kolmogorov complexity of X plus the Kolmogorov complexity of Y given X. And this is just because if we have a program that prints X and we have a program that prints Y given X, then we can combine them to get a program that prints both X and Y. And symmetry of information in the time unbounded setting basically says that this inequality is tight in the sense that the Kolmogorov complexity of X and Y is at least the Kolmogorov complexity of X plus the Kolmogorov complexity of Y given X minus some small term. And now if we combine the two inequality above, then we get something looks like this, which is analogous to what is also called symmetry of information in Shanlong's information theory. And sometimes people call this the chain rule, but we will just call it symmetry of information. Yeah, we have symmetry information for time unbounded Kolmogorov complexity. So the question is whether symmetry of information holds in the time-bounded setting. So for example, can we show that the KT complexity of X and Y is at least the K poly T complexity of X plus the K poly T complexity of Y given X. minus some order log term. Yeah. And then here we're allowed to have a polynomial overhead in the time bounds on the right hand side. So this makes the right hand side smaller. And it turns out that the time-bounded symmetry of information is unlikely to hold. So there's a work by Lompret and Watanabe. So they show that if one-way functions exist, then we don't have symmetry of information for KT. And the proof requires a little bit of work, but the intuition is very simple. So let's consider one-way permutation for simplicity. So if we have like one-way permutation F, and given x, we can compute f of x efficiently. But given f of x, we cannot get back x efficiently. So although these two string contains all the information about each other, but there's an asymmetry between them when taking into account the time. This is the intuition why if one-way function exists, then no symmetry of information for KT. But this result only shows one direction, and we don't know if the failure of symmetry of time-bound symmetry of information implies the existence of one-way functions. And it was an open question to show some if and only if statement between one-way functions and symmetry of information.
Can you sketch how symmetry of information is proved in the unbounded setting?
Oh yeah, I cannot recall the details, but it involves some exhaustive search. So it crucially relies on the unbounded feature of Kolmogorov complexity. So you cannot extend it in the to the time-bounded case. Okay, let's take a step back and review the definition of one-way functions to see what might be the issues to establishing an equivalent between one-way function and symmetry of information. So usually when talking about one-way function, we just say that a function is one way if it is easy to compute and hard to invert. But in the more formal definitions, it just says that it's hard to invert for almost all inputs, not every input. And it has to be hard against probabilistic adversaries. These are two important details in the definition of one-way functions. And then using the intuition that I just mentioned, so this leads us to think maybe we need to adjust the statement of symmetry of information in order to get an equivalence. And for example, instead of considering whether a symmetry of information holds for every pair of strings, maybe we should consider average pairs. So to reflect this fact, and also maybe we should consider some probabilistic version of time-bounded Kolmogorov complexity to address the fact that the definition of one-way function in the definition of one-way function, even trying to recover a pre-image using a probabilistic algorithm is not possible. Okay, now this leads me to talk about some probabilistic notions of time-bounded Kolmogorov complexity. So one such notion is called the randomized T time-bounded Kolmogorov complexity. So remember the KT definition. The KT complexity of a string is the minimum length of a program that prints the string deterministically in T steps. And then here, the rKT complexity of a string is the minimum length of a randomized program that prints the string with probability at least 2/3. So there's a fixed program, a randomized one that outputs the string with high probability over its internal randomness. So this is rKT. And another slightly more complicated notion is called probabilistic T time-bounded Kolmogorov complexity. or PKT. So okay, the PKT complexity of a string X is defined as the minimum K such that with probability at least 2/3 over a random string W, there's a program M that takes W as an input and prints X. So unlike in the previous cases where we have a fixed program that prints X, so either a deterministic one or randomized one, here we say that for most random strings, there is a program that prints X, and the program can depend on the random string. So in this case, it's like a probabilistic encoding of X, where the encoding depends on the randomness, and instead of a fixed encoding. Now let me state our results more formally. We show that one-way function do not exist if only if average case symmetry of information for rKquasipoly holds. So average case symmetry of information for rKquasipoly means for every polynomial time sample bit distribution D over 2n bits. And for every sufficiently large T that is greater than some polynomial, there are infinitely many n such that with high probability over a pair of strings X and Y, such that symmetry of information holds for X and Y with respect to PKT. So in other words, the PKT complexity of X and Y is greater than the PKT of complexity of X plus the PKT of complexity of Y given X minus some order log term. So this is average case symmetry of information for PKT. And you may notice that in this case, we only say that average case symmetry of information hold for infinitely many n. And this is actually expected because if one-way function do not exist, it means we can invoke any function on infinitely many inputs. So in 2T, we should have only have time-bounded symmetry between pre-image and image on those input lengths. So this only infinity often if we can break one-way functions infinity often. But our result is like also robust in terms of this. So if we instead say the infinity often one-way function do not exist, then we have that the average case symmetry of information hold almost everywhere. So in the previous result, we use PKT to capture one-way functions or the long existence of one-way functions. And it turns out that we can also use rKT, but in this case, we have to move to the quasi-polynomial time regime. So we show that the quasi-polynomial time secured one-way functions do not exist if and only if average case symmetry of information for rKquasipoly holds. So here, everything is the same as before, except that T has to be greater than some quasipoly n. And we are talking about one-way function that is secured against quasi-polynomial time adversaries. Yeah, it's just normal one-way function that's secured against polynomial time adversaries. And correspondingly, we have polyheap. And by the way, we're talking about one-way function that is still polynomial time computable, efficiently computable, but its security is against quasi-polynomial time. Okay, now let's look at the proof, and we'll focus on the PKT case first. So we want to show that infinity often one-way function do not exist is equivalent to average case symmetry of information for rKquasipoly hosts. And what we're going to show is that these are both equivalent to something called average case conditional coding. And I will explain what it is. But before telling you what conditional coding is, I need to tell you about the original coding theorem in Kolmogorov complexity. So just like symmetry of information, the coding theorem is another important property of Kolmogorov complexity. So it says that if we have a computable distribution D that samples a string X with probability D of X, then the Kolmogorov complexity of X is at most log 1 over D of X. So if a string is sampleable, then we can encode it in short length. Again, this is for time unbounded Kolmogorov complexity, and we don't have such a coding theorem for K-poly. So even if we just consider efficiently sampleable distribution, we don't have a coding theorem for just K-poly. But luckily, if we consider PKT, then we do have a coding theorem. So with Oliveira and Zhenjian, we show that if we have a polynomial time sampleable distribution that samples a string X with probability of X, then the PK poly complexity of X is at most log 1 over D of X and plus some order log n term. So this is the optimal coding theorem for PK poly. Okay, another useful fact related to this is that for any distribution D, the Kolmogorov complexity, the time unbounded one, the Kolmogorov complexity is greater than, is at least the log of 1 over the probability of X, like with high probability over X sampled from D. So this says that the K complexity is at least this quantity. And below that, the PK poly complexity is at least the K complexity, like roughly. So by coding, we have that this is most this, and by this fact, we say that for most string, PK poly should be greater than this. And then corollary just says that the PK poly of X is roughly equal to the log 1 over the probability of X with high probability when X sampled from D. So on average, these two quantities are the same. Okay, now what is conditional coding? So conditional coding says that for every polynomial time sampleable distribution D, which now is on 2n bits, so it samples a pair. And for every pair X and Y in the support of D, the PK poly complexity of X given Y is at most log 1 over the probability of X conditioning on Y. And we call it a conditional coding because here we want to relate the PKT complexity of X given Y to the probability of X but conditioning on Y. So that's conditional coding. And again, we can define the average version by saying that the conditional coding holds for X and Y with high probability when X and Y are sampled from the same distribution D. Yeah.
This is the definition.
Definition, yeah, we don't have it.
Is this a statement? Is it a statement or a definition?
Definition. So this is definition. Oh, okay. Conditioning coding means this thing. So it's a lot of theorem. We don't claim that this is true.
So conditional coding holds when this is true.
Yeah.
Okay.
Yeah, this means conditional coding holds, but we don't know whether it holds or not. But as you see, probably it doesn't. Yeah. And this say worst case. So for every X and Y in the support, we say that the PKT complexity of X given Y is at most log 1 over the probability of X conditioning on Y. And this is the average case where we consider an average pair from the distribution, the same distribution.
So what do you mean by D that's given Y?
Yeah, so this D is also this D. So this D is over 2n bits. So it samples X and Y. Now I give you Y. What's the probability of seeing X? Conditioning on that, you're seeing Y. Yeah, we're always conditioning on the Y pass. Yeah, so this conditional coding. And, actually, as I just claimed earlier, average conditional coding is equivalent to okay, this conditional coding. Okay, as I claimed earlier, so one-way function do not exist if and only if average conditional coding holds. That means if one-way function exists, then average then conditional coding shouldn't hold. So even though we have coding for original coding, but we probably don't have conditional coding. And you may be wondering why we cannot use the original coding theorem to show the conditional coding theorem. And this is because the conditional coding theorem, the conditional coding theorem can be viewed as we are trying to encode a string X, where X is sampled from some conditional distribution of D that is conditional on some string Y. So even though the joint distribution of D is polynomial time sampleable, but the conditional probability distribution may not be polynomial time sampleable when you're conditional on some string. So we cannot apply the original coding theorem to this conditional distribution because the original coding theorem only works for polynomial time sampleable distributions.
If you ask them one of them doesn't exist, then you should have the conditional distribution is actually sampleable.
You are 10 slides ahead of me, but
Okay, which of these, if let's say one-way permutations exist,
yeah,
which of these is not true? You can easily see that it's not true.
you cannot easily see it, but neither of these will be true if you assume one-way function.
Neither of them.
Neither of it, because one is stronger than the other. So neither of this. So if one-way function exists, even on average, you don't have conditional coding. So if you don't have it on average, you don't have it in the worst case. Okay, as I claimed earlier, the average case conditional coding is equivalent to average case symmetry of information. So let me show you the proof of this. So it's very simple. So let's fix the polynomial time distribution D that samples the pair X and Y. So on the top, we have average case conditional coding, and we want to get average case symmetry of information at the bottom. Now, first of all, let's remove the probability and just keep in mind that we are dealing with an average pair X and Y sample from D. And we then identify the common quantity in both expressions, which is rKquasipoly of X given Y. And then we just rearrange things a little bit to make them more alike. So nothing happened yet at this point. Now on the top, we have probability of X conditioning on Y. And we can rewrite it as the ratio between the joint probability of X and Y and the marginal probability of Y. So here, D to the 2 denotes the marginal distribution, of Y on the second half. So this conditional and just the joint distribution and the marginal distribution. And now we have got rid of the conditional probability. So let's rearrange things a little bit further. So now the bottom 2 lines looks like kind of similar. And remember what I said earlier. So once we have conditional coding, like the original one for rKquasipoly, we can say that for any polynomial time sample distribution, the rKquasipoly complexity of a string is roughly equal to the log of 1 over the probability of the string with high probability, which is here. So this means these two things, and here, because both D and the marginal distribution of D are polynomial sampleable. So by the coding, we actually have that these two quantities should be about the same, and these two quantities are also about the same, at least on average. So basically, this completes the proof because we can just replace this one with this one, and this one and with this one, and this is image of information. And this shows the forward direction, but the proof of the other direction is exactly the same. We can just reverse the previous argument, and we won't get into the details. So now we have shown average case conditional coding is equivalent to average case symmetry of informations. So it remains to show the equivalent between the long existence of one-way function and average case conditional coding. And we're going to do one direction, then let me try to give some high-level description of the proof of the four directions. So assume that we can invert one-way function like almost everywhere. We want to show that if high probability over a pair x and y sampled from distribution D, then conditional coding holds for x and y, which means what is written here. And remember earlier, we talked about using the original coding theorem for rKquasipoly to show a conditional coding theorem. And the reason why it didn't work was that the coding theorem can only be applied to efficiently sampleable distribution. But here we are dealing with the conditional probability distribution of D, conditioning on some string y. And then the conditional distribution may not be polynomial sampleable, even though D itself is polynomial sampleable. Now, as Hanin pointed out, now things are a little bit different because we can invert one-way functions. So with this assumption, we can hope to sample the conditional distribution efficiently. And in the work by Palazzo and Luby and by Palazzo and Levin, so they show that they showed something called an extrapolator under the assumption that one-way function do not exist. So if infinity of one-way function do not exist, then for every polynomial sample distribution D, which again samples a pair x and y, then there's an efficient randomized algorithm that given y, that approximately samples the distribution D conditioning on y for almost all y.
So I actually don't understand why you need the paper with Levin, not just the paper with Luby.
Yeah,
So
just to be
that
safe
already
cycle.
says that, exactly.
Because
that.
when I was looking for like this theorem, they usually cycle. But I didn't even, I had a hard time finding a proof of this thing, but eventually I found it in Russell's thesis. So I'm not sure which one is the correct citation. But maybe just impossible.
There was a 6-page Fox. It was a limited Fox of 1.6 pages. You can always blame it on Svigali.
Yeah. But there's a proof available in Russell's thesis.
Oh, you probably also like read like
look there
monograph.
What he writes about my driving.
It's all true, but I didn't write it.
Okay, so basically it says that if one element do not exist, we can efficiently sample the conditional distribution, at least approximately, at least for most y. So basically that's what we need in order to apply the original coding theorem to get conditional coding. So we basically use the efficient extrapolator as a proxy for the conditional distribution. And because it's efficient, we can just apply the coding theorem to it. And with a little bit more work, we can show that this gives the average case conditional coding that we wanted. Okay, as I mentioned, we also showed an equivalent between the long existence of one-way function and the average case symmetry of information, but for for rKquasipoly. the proof that I just described use the original coding theorem for PKT, but we don't have a coding theorem for rKT. So actually, for this one, we need to use a different approach. And I will not talk about the detail, but the starting point is the recent result by Ilango, Ren, and Santana. So they show that if one-way function do not exist, then there's a heuristic for approximating the K complexity. And like we have seen in some of the previous talks, we can use such a heuristic as some kind of a distinguisher and combine it with certain generator that has an rKT style reconstruction property that have a reconstruction procedure. And this will allow us to show that the rKT complexity and the K complexity are very close on average. So these two are very close on average. Now then we can just take the symmetry of information theorem for time unbounded K complexity and replace K with rKT. And then this will give us an average case symmetry of information for rKT. And actually we did the conditional variance of these measures, but we'll not get into the details. But one reason that we only get the quasi-polynomial time is because the generator that we use here has some like polylog overhead in terms of the advanced complexity. So we can only show that like rKT and K are equal up to some polylog additive terms. So in this case, we don't get the optimal symmetry of information for rKT. So that's why we need to go to the quasi-polynomial time regime. Finally, I want to mention some other results that we have in our paper. So I just show you in this talk that we can characterize the long existence of one-way functions using average case conditional coding and average case symmetry of information. But in the paper, we also show that they are equivalent to something called average case conditional language compression, which is some version of the language compression theorem in Kolmogorov complexity. So language compression is another like important property of Kolmogorov complexity. So this for the case where one-way function do not exist. And we can also characterize NP is contained in BPP using this case worst case conditional coding and language compression. And similarly for NP is easy on average, we can characterize it using another kind of average case version of the same property called independent average case. But I guess I will not define it here. But the idea is that this gives a way to look at this standard complexity assumption through the lens of Kolmogorov complexity and its properties.
Do you have any characterization of NPE average? I mean, error.
Yeah, we do have some version. Like, yeah, but it's a little bit hard to explain that version. It's called the certifiable version.
Oh, I see.
Yeah, we can talk more about it. One thing that you may notice is that we only have symmetry of information in the one-way function case, and we don't have it in the other two cases. So this is an exceptional case where we can use symmetry of information to characterize it. And so
oh, that's another concern.
Yeah.
Okay, whether it's like AM in BPP or AM in BPP.
AM in BPP.
Yeah, instead of BPP.
Oh. That we.
Shouldn't that be equivalent?
Yeah.
Oh, I see.
Oh, okay. Maybe. Yeah.
Oh, yeah.
Yeah. Okay, yeah. For example, we don't know whether worst case symmetry of information. We don't know whether we can use worst case symmetry of information to capture NP is in BPP. We only know that NP is in BPP implies worst case symmetry of information. And in fact, assuming NP is average case easy errorless, suffice to give you worst case SOI. So then the interesting question is, what can worst case symmetry of information characterize? Now it's just sandwich between NP is average case easy and low one-way function, but we don't know what it can like characterize exactly. I think this.
Questions?
Could you go back to the previous slide? So that's worst case symmetry of information for PKT?
In this case, yeah. In this case, everything is stayed with respect to PKT.
Okay. So we know under a de-randomization hypothesis, PKT and KT are roughly the same. And we know that in the worst case, symmetry of information provably does not hold for KT. So is there
Okay.
You're
There's
suggesting kind of a win-win.
When you say worst case symmetry of information doesn't hold for KT,
right?
you are talking about Levin's notion of KT. So
Oh, that's right. Yeah.
so here we are talking about the
different
K
KT.
superscript T.
Right.
It's the other word.
So you don't know how to do any of this for PK superscript T.
PK superscript T.
Yeah. Or no, PK lower. So the probabilistic
It
version of
isn't
Levin's complexity.
Yeah, that notion has not been investigated much.
Right.
But I believe that all of this holds for PK little t. If you define the notion of PK little t correctly. But still, that doesn't give you any unconditional result because we don't know how to refute symmetry of information for PK little t. So the only result, the only thing that we know is we can refute worst case symmetry of information for Levin's K little t. That's the only result that we know about time-bounded symmetry of information unconditionally.
So I assume every time you're talking about one-way functions here, you're talking about one-way functions secure against uniform polynomial time adversaries. Is there a natural way to translate this for non-uniform one-way functions, like maybe like p-polysamplable or something like this?
P-polysamplable. Oh, you mean here when you say average case, and then you talk about one-way function, the distribution corresponds to the one-way function, but the adversary corresponds to the notion of Kolmogorov complexity. So when I say the one-way function is secured against non-uniform adversaries, you need to change the Kolmogorov complexity notion. And I believe we have talked about this with my co-authors. We can somehow characterize them using some conditional version of symmetry of information, which may not be easy to state, but maybe it's possible.
Yes.
Questions? Thank you. Should take 1 minute and a half.